Good morning. Can you hear me? Hello? Can you hear me?
Yes.
Okay, good. All right, so last time we talked about the prime numbers and composite numbers, and today we're going to talk about divisibility. So let's one of the most important theorem about divisibility is that if you have two integers, say one of them is positive, then you can always write one integer is equal to the positive integer times another integer plus a remainder. Okay, to be more precise, let's look at the statement of the theorem. So let A and B be integers. Let B be greater than 0. So A can be a negative integer, but B is positive. Then there exists two integers. There exists a Q and R, so that A is equal to B times Q plus R. And R is strictly between 0. R is greater than or equal to 0, strictly less than B. So in this case, Q is called the quotient. And R is called the remainder. Okay, so in other words, the theorem tells you you can always write an integer A as B times the quotient plus the remainder. But one thing you have to pay a lot of attention is this restriction. So the remainder is always greater than or equal to 0 and strictly less than B. So this is the key for this theorem. And so before we prove the theorem, let's recall the notation. So the notation, this floor function, say A over B, so this is the floor function. Well, let me just don't write A over B, just write an arbitrary number, say S. This is floor function, which is the greatest integer less than or equal to s. Okay, so for example, what is, say, 3.1? So the greatest integer less than or equal to 3.1 is, of course, 3. And say 4. So the greatest integer less than or equal to 4 is just itself. And what about this? So the floor function for negative 2.3. So what is the greatest integer less than or equal to negative 2.3? Then this is equal to negative 3. Okay, so this is the definition of the floor function. So to prove this remainder theorem, we need to use floor function. So let's look at the proof of the theorem. Okay, so we have two integers a and b, and b greater than 0. So we just let q be the floor function of a over b. And of course, this q is well defined because b is greater than 0. So a over b is clearly a real number. And let just r be a minus b times q. So the proof is very constructive. We just construct q and r. So what's remaining is to show that this r satisfies the restriction r greater than or equal to 0 and strictly less than b. And it is clear that this implies, so we get a is equal to b times q plus r. So this is just come from this definition of r. So this equation holds. So we only need to show that we just want to show r is greater than or equal to 0, strictly less than b. Okay, so one of the things we have to remember that is for the floor function. So the floor function is the greatest integer less than or equal to this number. So in particular, the floor function plus 1 is always strictly greater than this number. All right, so this is what I'm saying. Okay. Since q equals to a over b is the greatest integer less than or equal to a over b. So we have q plus 1 must be greater than a over b. Because if q plus 1 is less than or equal to A over B, then Q cannot be the greatest integer less than or equal to A over B. So what we get is now this Q is less than or equal to A over B, but greater than A over B minus 1. So this comes, the left-hand side comes from here. This tells you Q is greater than A over B minus 1. Okay, now we can multiply B to this inequality. Since B is greater than 0, when you multiply B, the direction of the inequality doesn't change. So this implies if you multiply a B to both sides, B times Q is less than or equal to B times A over B. So what is this? So if you compute, then this is A minus B is less than BQ less than or equal to A. Okay. Okay, now the right-hand side, if you look at the right-hand side of this inequality, so the right-hand side would imply A minus BQ is greater than or equal to 0. But by the definition, R is equal to A minus BQ. So this implies R would be greater than or equal to 0. So this is one thing. Because we want to show R is greater than or equal to 0, strictly less than B. Okay. On the other hand, if you look at this left-hand side of the inequality, so this implies implies A is less than BQ plus B. Okay, and if you move BQ to the left-hand side, this implies A minus BQ is less than B. But A minus BQ is by definition equal to R. This implies R is less than B. So these two things would imply R is greater than or equal to 0, strictly less than B. Okay, so this finishes the proof. So we are done. So you can see this is one of the most important theorem for the remainder theorem. So the remainder is strictly less than B, greater than or equal to 0. So do you have any questions about the proof? Okay, so one thing I forgot to say in the theorem is once you have such a representation, A equals to BQ plus R, for R greater than or equal to 0 less than B, then this representation is unique. So you have only one way to write A as such a sum. So this is what we are saying. I'm saying, okay? So let me write it. So moreover, if A is equal to B times Q plus R with R greater than or equal to 0 less than B, then this representation is unique. In other words, you have only one way to write A as BQ plus R. Okay, so let's prove it. So proof of uniqueness. So we'll prove that if we have two different representations, then these two representations have to be the same. So suppose there are two representations. That is A equals to B times Q1 plus R1 with R1 between 0 and B. And equal to B times Q2 plus R2 with R2 between 0 and B. Okay, since these are two representations, different representations, we can assume R1 is not equal to R2. In particular, we may assume R1 is greater than R2. Well, of course, you can also assume R2 is greater than R1, so it doesn't matter. So anyway, since these are two different representations, the R1 and R2 cannot be equal, because if R1 equals to R2, these are the same representation. So we can assume R1 is greater than R2. Okay, now you just subtract these two equations. So we subtract two equations. So when you subtract two equations, what you get is on the left-hand side is 0. On the right-hand side is B times Q1 minus Q2 plus R1 minus R2. Okay. And here, then what you get is this implies B times Q2 minus Q1 is equal to R1 minus R2. Well, you should remember this is greater than 0 because R1 is greater than R2. Okay, this is because we just move B times Q1 minus Q2 to the left-hand side. So you just change the sign, and you get B times Q2 minus Q1 is equal to R1 minus R2. Okay, now if you look at this equation, this tells you R1 minus R2 is a multiple of B. In other words, B divides R1 minus R2. So this implies B divides R1 minus R2. Okay, so remember B is positive. B is positive, and R1 minus R2 is also positive. So by our previous theorem, we know that then B would be less than or equal to R1 minus R2. Okay, a divisor, a positive divisor is always less than or equal to the original positive number. And this implies B plus R2 is less than or equal to R1. But this is a contradiction because we know that R1 is strictly less than B. However, here we showed that R1 is greater than or equal to B because R2 is greater than or equal to 0. But this contradicts. With R1 is less than B. Okay. So this tells you there can be two different representations, okay? Because if you have two different representations, you get a contradiction. All right, so the remainder theorem gives us a unique representation for Earth. Okay. All right. Okay, so an immediate corollary tells you that a number d divides a given number n if and only if the remainder for d divides n is equal to 0. So this is a corollary. The number d divides n if and only if on division of n by d, the remainder is 0. Okay, I think this proof is simple now. So if the remainder is 0, then the theorem tells us n would be equal to d times q plus 0. So this implies n is just equal to dq. So this would tell you by definition, d divides n. Okay. On the other hand, so if d divides n, then n is equal to dq by definition. Okay, now we need to use the previous theorem here because this representation is unique. So this is, well, this is equal to plus 0, okay? So by previous theorem, the remainder is 0. All right. So once the remainder is well defined, we have a notation. We have a notation here. So the definition is for, say, an integer b greater than 0, we can define a, we use triple bar is equal to r and write mod b to mean that the remainder on division of A by B is odd.
Did you hear me?
Yes. So you have
what
yeah.
is this? What's that word before the B at the very bottom in parentheses?
So say it again. So can you speak a little bit louder? It's
Yeah. So at the bottom in parentheses, the A and then the triple bar.
Oh,
What's
that
that?
is MOD, mod B,
Okay.
modular. Okay.
Okay. Thank you.
Mm-hmm. Okay, so a general notation. So a general notation for this is so in general. So in general, we write, say, A equal to C mod B if A and C have the same remainder when dividing B. When dividing B. When divided by B. Okay. Okay, so this notation just means they have the same remainder. Mod B, modular B. Okay, so let's look at a few examples to compute this remainder. For example, so we have, if you look at 23, so if say mod 7, oh, mod 7. So what is the remainder for 23 mod 7? So you divide 23 by 7. So you get the quotient is 3 and the remainder is 2. This is because 23 is equal to 3 times 7 plus 2. So recall this 2 really satisfies. So 2 is greater than or equal to 0, less than 7. So this is important. You have to make it this way, because you can also write this 23 is equal to 2 times 7 plus 9. But this 9 is not the remainder, because the remainder has to be strictly less than 7 and greater than or equal to 0. So this is the remainder, right? Okay. Now let's look at another one. So what about, say, negative 4 mod 5? So can anyone tell me what is the remainder of negative 4 modular 5? So what is the remainder? So anyone knows the answer? What is the remainder of negative 4 modular 5? Now, you remember the remainder is always greater than or equal to 0 and less than 5. So if you want a remainder, so this is a key as I addressed, the remainder is greater than or equal to 0, less than b. So here the b is 5. So you need to find the r between 0 and b. So that's the key. Okay, so the key is to write, so negative 4 is equal to what? Well, this is negative 1 times 5 plus 1. Okay, so if you write negative 4 as this, then this is a remainder because 1 is indeed between 0 and 5. So this is important. Okay, 1 is between 0, so this is 1. The remainder is 1. All right, I think for positive numbers, it's easier, but for negative numbers, you have to be a little bit careful because the range of the remainder is essentially the most important thing about the remainder theorem. So let's look at another example. So negative 14. So we want the remainder of mod 6. So what is the remainder for negative 14 modulo 6? So think about it. 4, because all right, that's great. That's great. Okay, we write negative 14 is equal to negative 3 times 6. Well, this is plus 4. So this 4 is indeed greater than or equal to 0, less than 6. So the remainder is 4. All right. So of course, you can also write it as negative 2 times 6 plus negative 2, but this negative 2 doesn't satisfy this inequality here. So negative 4 is not a remainder. So you have to make sure the remainder is in this range. All right, so this is the example for this remainder theorem. Okay, so next we talk about the greatest common divisor. So the greatest common divisor. So here is a definition. So an integer is a common divisor of two other integers if it divides both of them. So we write C of AB as the set of all common divisors all common divisors of A and B. So what is the greatest common divisor? So the greatest common divisor of two non-zero integers is the maximal element in C of AB, so in the set of all common divisors of A and B, which is denoted by greatest common divisor, GCD, of AB. Okay, so it follows from the definition, if you want to find the greatest common divisor of A and B, so you need to first find out what is the set of common divisors, CAB, and then you just choose the largest element in C of AB, and you get the greatest common divisor. Okay, so let's look at a simple example to see how we use the definition to find out the greatest common divisor. Find the greatest common divisor of 18 and 30. So to find out the greatest common divisor, let's first find out the set of common divisors of 18 and 30. So what is the set of divisors for 18? So first, so for 18, the divisors are of course 1, and always remember there's -1, and 2, -2, 3, -3, 6, -6, 9, -9, and we also have 18, -18. So these are all the divisors for 18. And for 30, so the divisors are again 1, -1, 2, -2, 3, -3, 5, -5, 6, -6, and 10, -10, 15, -15, and 30, -30. Okay, when you write out all the divisors for 18 and 30, you can find out what is the set of common divisors of 18 and 30. Okay, so you get 1, -1, and 2, -2, 3, -3, and Okay, 6, negative 6. Okay, these are all the common divisors.
Would we be allowed to just write it out as plus or minus 1, plus or minus 2, or do we need to list them individually?
You can write plus or minus 1, plus or minus 2. That's fine. Okay. Yes, I just write it out to make it clearer. Okay. Okay, so now what is the greatest common divisor of 18 and 30? So you can see, well, 6 is the largest. 6. Well, of course, to find the greatest common divisor, you may also just need to list all the positive common divisors because the divisors always appear as pairs. You have a positive divisor, then you also have a negative divisor. But since you are finding the greatest common divisor, you always choose the positive one. Okay, you can also use this notation. So C plus AB, this means the set of or positive common divisors of A and B. So in this situation, the greatest common divisor always comes from this C plus of A and B. So you don't have to each time to list all the negative counterpart. You just look at the positive divisors, okay? That's okay. But this is only for finding the greatest common divisor. But if in some other problems, you may want also negative divisors, then you have to be careful. All right, so the first lemma is clear from the definition. So we don't even need to prove because the greatest common divisor of A and B is equal to the greatest common divisor of B and A. So this is because the set, because C of AB is of course equal to C of BA. So when you talk about the set of common divisors, the order of these two numbers doesn't matter. So C of AB equals to C of BA, so the largest element in the set would be the same. Okay, so the second lemma is the greatest common divisor of A and B is equal to the greatest common divisor of the absolute value of A and absolute value of B. So this is because once some number divides A, this is equivalent to say this number divides the absolute value of A. So you can always put the plus or negative signs in front of the divisors. So you can always change those numbers to positive numbers. For example, just now the greatest common divisor of 18, 30 is of course equal to the greatest common divisor of negative 18, 30. It's also equal to the greatest common divisor of negative 18, negative 30. Is also equal to the greatest common divisor of 18, negative 30. So you have freedom to put signs in front of the numbers. However, the greatest common divisor is always equal to 6. Okay. So this is what this lemma tells you. Okay, so the next lemma is very useful, especially when proving harder theorems. So suppose we have, if A is not equal to 0 or B is not equal to 0 are integers, then the greatest common divisor of A and B would always satisfy this inequality greater than 0 and less than or equal to the minimum of the absolute value of A and absolute value of B. Okay. Okay, so let's look at the proof. So we first proved the greatest common divisor of A and B is always greater than 0. So since 1 divides A and 1 divides B, so 1 belongs to the set of common divisors of A and B. But the greatest common divisor of A and B is the maximum element in C of AB. In particular, the greatest common divisor of A and B would be greater than 1. So the greatest common divisor of A and B would be greater than or equal to 1. And in particular, this is greater than 0. Okay, so this is one side. One side of the inequality is easy. Now let's look at the other direction. Okay, so by definition, the greatest common divisor of A and B is indeed a divisor of A and B. So for simplification, so let's write D is equal to the greatest common divisor of A and B. And by definition, so we know that the greatest common divisor is a divisor, so D divides A and D divides B. Now, since we've already proved that if you recall the theorem we proved earlier, if D divides A and D divides B, then D divides the absolute value of A and D divides also the absolute value of B. And by our previous theorem, so we have D divides the absolute value of A and D divides the absolute value of B. Now, since D is since D is greater than 0, this is what we just proved. And the absolute value of A and absolute value of B are also greater than or equal to 0. So hence we have D is less than or equal to A, absolute value of A, and D is less than or equal to the absolute value of B. But this is exactly means D is less than or equal to the minimum of the absolute value of A, the absolute value of B. Okay, D is less than both of this, then D is less than or equal to the minimum. All right, so this lemma is particularly useful when you try to find the greatest common divisor of two numbers. One of them is very big, the other one is smaller. So you just need to check the divisors for the smaller ones, okay? You don't have to check the larger one because the greatest common divisor is always less than or equal to the minimum of these two. So let's look at an example. Find the greatest common divisor of 48 and 732. Okay, so how to find out this? You see, one is 48, the other one is 732, but 732 is relatively bigger. So to find out the greatest common divisor, so you know that this, so again, we'll let D be the greatest common divisor of 48 and 732. So by our lemma, so we have D is less than or equal to the minimum of 48 and 732. But this is 48. So the greatest common divisor is less than or equal to 48. So to check it, we may want to see if the largest 48 is divisible by 732. So let's check. So 732 divide 48. So this is 1, 48. So what you get is 5, 2. Is it divisible by 48? So 5. So this is not divisible by 48. So you have to check other divisors of 48. So let's look at the other divisors. So for 48, the set of positive divisors are, so of course you have a 1, 2, 3, 4, 6, 8. Okay. We have 12, 16, 24, 48. So just now we've seen that 48 is not a divisor of 732. So now you have to check the 24. Let's say, look at the 3. This is 72. So this is not a divisor because we have 12. Okay. 30. So then you look at 16. This is 4, 64, 92. So again, this is not a divisor 16. So what about 12? Okay, 12 is indeed divisible by 732. So this implies the greatest common divisor of 48, 732 is just equal to 12. So you just need to check for the smaller number. But still, if you look at this example, still this method is not so pleasant because you still have to check a lot of divisions to find out the greatest common divisor. If these two numbers are big, it takes a lot of time to find it out. So we'll develop a much more efficient way to compute the greatest common divisor later. Okay.
Question.
Yes.
Would you want us to show our work for each number we try?
No, I don't think so. I don't. You just need to try it on a scratch paper. But as I said,
Okay.
later we are going to have a better way to compute the greatest common divisor. Okay. So this is just a primitive way to compute the common divisor, greatest common divisor. All right. Next, we introduce another notion you probably have seen in many places. That is, two numbers are relatively prime or co-prime. So definition. So two integers are relatively prime or co-prime if the greatest common divisor is 1. Okay. So for example, if you look at four and 9, so this pair, so because the greatest common divisor of 4 and 9 is equal to 1, so they are co-prime, okay? They are co-prime. But if you look at 6 and 18, then it's clear the greatest common divisor of 6 and 18 is equal to 6, so they're not co-prime. Okay, they're not co-prime. I think this is a very commonly used notation. So the next lemma tells us that if G is the greatest common divisor of A and B, then you can divide both A and B by G and claim that A over G and B over G are co-prime. So if G is equal to the greatest common divisor of A and B, then the greatest common divisor of A over G and B over G is equal to 1. In other words, A over G and B over G are co-prime. So roughly speaking, so if you know the greatest common divisor of A and B, once you divide G, you essentially remove the greatest common divisor. Okay, so their greatest common divisor becomes 1, so they are co-prime. Okay, so let me prove it. Okay, so since we know that the greatest common divisor of any two integers is always greater than or equal to 1, so let's, we can let K to be the greatest common divisor of A over G and B over G, and then we'll show K is equal to 1. But before that, let's make a preparation. Since G is the greatest common divisor of A and B, so this implies G divides A and G divides B. The greatest common divisor is a divisor. So A over G and B over G are integers, because only for integers we have the greatest common divisor. And then we can let K be the greatest common divisor of A over G, B over G. So we know that K is always greater than or equal to 1. All right, because the greatest common divisor we just proved is greater than 0, but since the greatest common divisor is an integer, so it has to be greater than or equal to 1. So we'll show actually K is equal to 1. Okay. Okay, let me write down what the notations are. So this notations are K is equal to the greatest common divisor of A over G, B over G, and G is the greatest common divisor of A and B. Okay, these are the notations. Okay, let's continue our proof. All right, so okay, since K is equal to the greatest common divisor of A over G, B over G, in particular, we know that K divides A over G and K divides B over G. Since K divides A over G, so there exists S and T such that A over G is equal to K times S, and B over G is equal to K times T. This is by definition of divisibility. Okay, if we multiply a G, and we get A is equal to k times g times x, and b is equal to k times g times t. So of course we can put the parentheses here. So that is k times g divides a, and k times g divides b. So k times g belongs to the set of common divisors of a and b. Kg divides both a and b. Now you can see that if k is strictly greater than 1, then k times g would be greater than g, because g is the greatest common divisor of a, b, which is positive. So if you multiply a number k which is greater than 1, you know k times g is greater than g. But this is contradicts with the maximality of g. Okay, because kg is a common divisor of a and b. If kg is greater than g, g cannot be greatest common divisor. So hence, k has to be less than or equal to 1. But since k is also greater than or equal to 1, as we mentioned, we have k is equal to 1. So that is the greatest common divisor of a over g, b over g is equal to 1. Okay, so do you have any questions about this lemma? Okay, so corresponding to greatest common divisor, we have another notion called the least common multiple. Okay, least common multiple, we only talk about the positive multiples, okay? We don't talk about the negative multiples. Otherwise, there's no least common multiple. So definition. The least so the least common multiple of two integers is the smallest, okay, positive integer, which is the multiple of both numbers. Okay, here, this is important. When you talk about least common multiple, you always mean in the set of positive multiples, because the reason is, if you look at an example, so if you look at, say, 2 and 3, of course, when you talk about multiple, you can say, always say -6, -12, -18, and those are also multiples of 2 and 3. There's no smallest such number. So when you talk about least common multiple, you always restrict to positive multiples. Okay, so for 2 and 3, the positive multiples are, of course, 6, 12, 18. And the least common multiple is 6. Okay. And we use the least common multiple of A and B to denote the least common multiple of A and B. Okay, so in this situation, we write LCM of 2, 3 is equal to 6. It's equal to 6. And of course, the same as for the greatest common divisors, the signs for A and B doesn't matter. So you can always look at the positive counterpart. For example, the first lemma is the least common multiple of A and B is, of course, just the least common multiple of the absolute value of A, absolute value of B. Okay, because if you put a signs in front of a multiple of A and B, it's still going to be a multiple of A and B. So the signs in front of the multiple doesn't change the multiple. It's just change the absolute value. And the similar lemma is that the least common multiple of A, B would always be greater than or equal to, of course, the maximum of the absolute value of A, maximum value of B, because the least common multiple of A and B is a multiple of A, is also a multiple of B. So in particular, it is a multiple of absolute value of A and the multiple of absolute value of B, and the theorem would apply. So let's look at the proof. So we'll let, say, K be the least common multiple of A and B. So K is a multiple of A and B. That means, so A divides K and B divides K. Hence, we have the absolute value of A divides K and absolute value of B divides K. So remember, K is positive, so the greater than or equal to 0 and the absolute value of A and absolute value of B are greater than 0. So our theorem tells us that we have the A is less than or equal to K and B is less than or equal to K. Therefore, we have K is greater than or equal to the maximum of B. Okay, so let's look at a example of how to find the least common multiple, and then we're done. So find the least common multiple of, say, 12 and 18. So how to find the least common multiple? So we just write down the multiples of 12. So for 12, the positive multiples are so you can see 12, 24, 32, 48, 60, okay. And you have 72, and keep going. And then for 18, the positive multiples are, so you have 18, 36, and 54, 72, and you can keep going. But you can see, you just check both lists to find the smallest common divisor. Here, this is 72. So you get the least common multiple of 12 and 18 is equal to 72. Okay, so do you have any questions? All right, so if you don't have questions, so we'll stop it here today, and I'll see you on Thursday.
Okay, thank you.
Yeah, bye-bye.